Good evening, everyone. We are here to present our project titled Smart Campus Surveillance, Anomaly Detection and Classification. This project has been developed under the guidance of Professor Vaishali, and we, the team members, are Rohan Gunge, Ashish Varghese, Vanessa Nadar, and Neha Nair from the Department of IT at Don Bosco Institute of Technology. Ensuring security. In today's world, ensuring security in large-scale environments such as campuses, public spaces, and urban areas is a growing challenge. Traditional surveillance methods rely heavily on manual monitoring, where security personnel observe video feeds to detect anomalies. However, this approach has significant limitations. Human operators can experience fatigue, distraction, and cognitive overload, leading to missing critical events. Moreover, in large-scale surveillance networks, monitoring multiple camera feeds simultaneously becomes impractical. Their inability to detect anomalies faster poses security serious risk. Incidents such as fight, assault, and medical emergencies like collapses often go unnoticed or are identified too late for effective intervention. As a result, security teams struggle to respond promptly, leading to increased threat to public safety. To address this, researchers have explored automated surveillance solutions leveraging artificial intelligence and computer vision. These solutions aim to enhance situational awareness by analyzing video feed and detecting suspicious or anomalous activities. Some methods include motion analysis, network behavior recognition, and deep learning based anomaly detection. While CCTV networks are widely deployed, their effectiveness is limited by the dependency on human operators. Currently, existing solutions fall into three categories. First is manual monitoring by security personnel, which is labor intensive, prone to human error, and inefficient for large scale surveillance. Second is basic motion detection system, which can flag movement but lack the intelligence to differentiate between normal and anomalous activities. The third and last one is rule-based video analytics, which require predefined conditions for anomaly detection but fail to adapt to dynamic real-world scenarios. However, these solutions often face challenges such as high false alarm rate, poor generalization to unseen environment, and computational inefficiency. Given these challenges, there is a need for an intelligent automated anomaly detection system that overcomes the limitation of traditional surveillance methods. This brings us to motivation behind our project, developing an efficient and scalable model that could be used in existing surveillance systems to analyze video footage, detect anomalies, and classify them accurately.
Now let's look at some findings from the literature review we carried out. To develop a robust anomaly detection and classification system, we explored existing research in machine learning and deep learning for video surveillance. Our review includes journal articles, systematic reviews, and research papers covering various anomaly detection techniques, their classification types, and performance metrics. A systematic review published in IEEE Access analyzed 29 different machine learning models for anomaly detection. It highlighted the growing preference for unsupervised learning methods. However, this review did not evaluate computational efficiency or dataset diversity, limiting its practical application for real-world surveillance systems. A research paper in IEEE Transactions on Emerging Topics in Computational Intelligence introduced a privacy-preserving skeleton-based video anomaly detection method, avoiding appearance-based analysis. While this approach enhances privacy, the study lacked concrete accuracy benchmarks and struggled with generalization as it relied solely on human motion data. Another IEEE Signal Processing Magazine article proposed a statistical activity analysis method that detects anomalies without object tracking. This method demonstrated robustness in cluttered environments. However, a major limitation was its inability to classify detected anomalies into specific categories, which is crucial for security response. A journal article in an image and vision computing introduced IVADC, FDRL, an intelligent video anomaly detection model integrating faster RCNN for object detection and deep learning and deep reinforcement learning for classification. This approach achieved a high accuracy of 94.5% on the UCSD anomaly dataset, but suffered from significant computational overhead, making real-time deployment challenging. Another comprehensive review in an image and vision computing categorized deep learning-based video anomaly detection models into spatiotemporal and one-class approaches. While it highlighted key challenges such as dataset limitations and ambiguous anomaly definitions, did not propose methods to overcome these issues. Lastly, an IEEE Access review covered deep learning applications in video processing, including anomaly detection, crowd analysis, and activity monitoring. It examined architectures like CNNs, ResNets, and LSTMs, emphasizing accuracy improvements. However, this review did not focus on the feasibility of implementing these techniques in real-world anomaly detection systems. From our literature review, we identified several gaps that our project aims to address. First, while many studies focus on detecting anomalies, few classify them into distinct categories. Classification is crucial for effective security response, as different anomalies such as fights, assaults, or medical emergencies require different interventions. Second, computational efficiency is a recurring issue. Many deep learning-based methods, especially those involving reinforcement learning, have high processing demands, making real-time deployment impractical without optimization. Third, dataset diversity remains a challenge. Many existing models are trained on limited datasets, often specific to controlled environments. The lack of generalization affects real-world performance, particularly in dynamic settings like university campuses. Additionally, privacy concerns arise with appearance-based detection methods. While skeleton-based detection addresses their concerns, it lacks standardized accuracy benchmarks and struggles to generalize across different movement patterns. Lastly, ambiguous definitions of anomalies lead to inconsistent labeling and evaluation across different studies. The inconsistency reduces model reliability in distinguishing between normal and abnormal activities.
Next, we will explore how a solution addresses these issues and enhances security through advanced AI and deep learning techniques. To address the identified gaps in existing research, our project focuses on developing a machine learning-based anomaly detection and classification system for surveillance videos. The objective is to accurately detect and classify abnormal activities such as fights, assaults, and medical emergencies like collapsing by leveraging both spatial and temporal analysis techniques. The model we designed systematically detects anomalies and classifies them into specific categories rather than treating all anomalies as a single event. This classification is crucial because different types of anomalies require different responses. While many anomaly detection models are computationally intensive, we have optimized our approach to balance accuracy with efficiency, making it feasible for real-world applications. This solution is designed not only for deployment within new surveillance setups, but also for integration into existing security systems. Additionally, our results provide insights into the performance of different machine learning techniques, enabling further advancements in the field. However, it is important to clarify that our project's primary scope is model building and systematic validation on unseen video samples to evaluate accuracy, generalization, and performance. The trained model is integrated into a Flask-based user interface where users can upload videos for anomaly detection and classification. This UI serves as an interactive platform to visualize the results and validate the model performance in a controlled environment. Now that we have outlined our proposed solution, we will move on to the methodology, where we will discuss the step-by-step process involved in developing the system. Our approach follows a structured methodology. So now, let's walk through the key steps taken to build this solution. We began with requirement analysis, defining the project's objectives, scope, and selecting appropriate technologies that help. Next, data collection involved gathering surveillance videos containing both normal and anomalous events to build a diverse and representative dataset. To ensure consistency across different video sources, pre-processing was performed. where video frames were resized, normalized, and enhanced. Frame extraction was then applied, capturing key motion patterns by extracting frames at regular intervals. Once the frames were ready, we performed feature extraction using efficient BO. This step transformed raw pixel values into high dimensional numerical representations that preserved spatial and temporal information. The system was trained using a two-stage modeling approach. In model training, we first trained a multi-instance learning model to detect anomalies in videos at bag level. If an anomaly was detected, the video was passed to the temporal convolutional network (TCN) model for classification. The MIL model determined whether a video contained any abnormal activity, while the TCN model further categorized the anomaly into predefined types: collapse, assault, or fight. To ensure reliability, performance evaluation was conducted using multiple metrics, including precision, recall, and F1 score, assessing the model's ability to differentiate between normal and anomalous activities. To further improve results, optimization techniques such as hyperparameter tuning and overfitting mitigation strategies were applied. Finally, the system was made accessible through model deployment, integrating the trained model into a Flask-based web application that allows users to upload and analyze the new videos in real time. Now that we have a clear idea of the methodology, let's visualize how these steps are connected in a system's workflow. Moving on to the architecture. Let's first take a look at how a dataset is structured. All data is stored on Google Drive in an hierarchical format, ensuring systematic and efficient access during training. The dataset consists of pre-processed videos which are already resized and normalized with trained test fits. And extracted frames stored in directories corresponding to their category: normal, collapse, assault, or fight. Additionally, feature vectors extracted using efficient BO are saved as .npy files for fast retrieval. Now, let's walk through the model pipeline. The process begins when user uploads a video in .mp4 or .avi format, which is then pre-processed by extracting frames, resizing them, and applying necessary transformations. The processed frames are passed to efficient BO for feature extraction, where each frame is converted into a 1280 dimensional feature vector and normalized using L2 normalization to ensure stable numerical values. These extracted features are then fed into the multi-instance learning model for anomaly detection. Instead of classifying each frame individually, MIL treats an entire video as a bag of frames and predicts whether an anomaly is present. If no anomaly is detected, the video is classified as normal and no further processing is required. However, if an anomaly is detected, the extracted features are passed to the temporal convolutional network (TCN) model for classification. The TCN model consists of multiple layers of 1D convolutions with dilated connections, enabling it to capture long-term dependencies in video sequences. An attention mechanism highlights the most relevant temporal patterns, ensuring the model focuses on critical motion changes. Finally, a softmax layer outputs the probability distribution over possibly anomaly classes, categorizing the event as collapse, assault, or fight.
Now let's begin with the project demonstration. Initially, we have imported all the necessary libraries and modules we required for this project. The notable libraries such as OS, NumPy, and TensorFlow framework, including all the necessary modules such as Keras, which include all the optimizers such as Adam models necessary for our project have been imported here. The initial step is extracting frames from the videos. We use OpenCV's video capture to read videos and extract frames at regular intervals. The extract frames for all videos function iterates through the video directories, processing videos in batches to extract a fixed number of frames per video, that is 32 in this case. Frames are resized and padded to maintain aspect ratio and consistent size of 224 into 224 pixels. Next step is of feature extraction. After extracting frames, we use pre-trained EfficientNet B0 model to extract features from each frame. This model is known for its efficiency and accuracy in image classification tasks. The extract and save features in batches function handle this process, loading the model with pre-trained weights from ImageNet. It iterates through frame directories, loading each frame, pre-processing it using pre-processed input, and then using EfficientNet V0 model to predict the features. These features are then saved into batches to disk for later use in training of the classification models. Next step is training our anomaly detect classification model. For anomaly classification, we employ a multiple instance learning model. The build ML model function defines this model, incorporating dropout, L2 regularization, and attention mechanism to enhance the model's performance. Importantly, the model architecture is tuned using Keras tuner with a hyperband search strategy. Hyperparameters like the number of units in the dense layers, dropout rate, and learning rate are optimized to minimize validation loss. The mesh model is then saved for further training and evaluation. The main function orchestrates the entire process. It initializes data generator for training and testing, calculates the class weights to address class imbalance using scikit-learn computes class weight function, perform hyperparameter tuning, trains the model best model with optimal parameters, and finally evaluates the model's performance. Performance metrics such as classification report, confusion matrix, ROC, AUC, average precision, and precision recall area under the curve are computed and visualized using matplotlib and seaborn. These metrics provide insights into model's ability to distinguish between normal and anomalous events. Now, we trained another model to classify exactly the type of anomaly that has occurred. After binary classification, we further categorize the anomalous videos into specific types such as fights, assault, and collapse. This is a multi-class classification task. The feature extraction process using EfficientNet V0 that we did earlier remains the same, but the labels are now assigned to 0 for fight, 1 for assault, and 2 for collapse. We use temporal collaboration network TCN with attention mechanism for this task. The build TCN with attention model function defines the architecture including temporal blocks, attention blocks, global pooling, and a classification head. The training process uses class weights to handle potential imbalance in database. We monitor training progress and evaluate the model on the test data using metrics such as accuracy, loss, classification report, and a confusion matrix. The confusion matrix provides a detailed breakdown of the model's performance for each anomaly type. Now, let's move on to the results. During training, we sought to identify the best hyperparameter values that minimize the validation loss. The tuner initially reported a validation loss of 1.1654, though iterative exploration, the best validation loss is achieved was 0.8928. This indicates that our model has effectively learned patterns to distinguish between normal and anomalous videos, resulting in lower validation loss. For model evaluation metrics, we employed several metrics to assess model's overall performance. Test loss, a measure of how well the model performs on unseen data. Here, our model obtained a test loss of 0.8875, which is close to the best validation loss achieved during training. This indicates the model generalized well to new unseen videos. Test accuracy represents the percentage of videos correctly classified. We achieved a text accuracy of 0.7333, which approximately indicates that the model correctly identified the category normal or anomalous for approximately 73.33% of the test videos. We'll look the classification report to understand the model's performance across the two classes. Precision, a measure of model's accuracy when it predicts a video to be anomalous or normal. Both classes have the precision of around 0.74. Recall, the measure of model's ability to correctly identify all anomalous/normal videos. Both classes have a recall of around 0.74. F1 score combines precision and recall to provide an overall measure of model's performance for each class. Both classes have an F1 score around 0.74. The confusion matrix provide a more detailed picture of classification results, showing the true positive, true negative, false positive, and false negative counts for each class. We also use ROC, UOC, AUC, and precision recall area under the curve to further evaluate our model. These scores reflect the model's ability to distinguish between two classes with an area under the curve score closer to 1, indicating better performance. Our model has ROC AUC of 0.7417, an average precision of 0.6783, and a precision recall AUC of 0.8064, reflecting a reasonable level of discrimination. We will briefly review the performance of our multi-classification model for anomaly detection in videos. The model achieved a test loss of 2.82 and accuracy of 60%. That means the 60% of videos in the test set were correctly classified. Looking at the classification report, we see the precision, recall, and F1 score for each class, fight, assault, and collapse. For example, the model correctly identified 62% of the actual fight videos at fight precision out of fight videos. It is identified 82% of them recall. The F1 score combines precision and recall, showing the score of 0.71 for fight. The confusion matrix provides the visual representation of model's predictions. Each row represents the true class and each column represents the predicted class. For example, for fight, 22 fight videos were correctly classified as fight. However, the model classified 8 assault videos as fight. Diagonal entries represent the correct classification, while off-diagonal entries indicate the misclassification. Our model demonstrates the promising performance, and these metrics indicate a model that generalizes well, correctly classifies a substantial portion of test videos, and exhibits a good ability to differentiate between normal and anomalous videos and further classify them into individual categories. Now let's take a look at our Flask application. We have trained both the multi-classification model and binary classification model and uploaded it in our local VS Code file in our Flask application. We have created a useful user interface that enables user to upload the surveillance footage. Now, this is the test video that we are going to upload. Once we have uploaded the video, we will press the upload button. As you can see, the processes that we mentioned of frame extraction and feature extraction are running in the background. Once the entire classification process is done, we can see the result in front of our screen. As you can see, there's a fight occurring in this video. So the anomaly detected was flagged as yes, and it was further classified into a subtype such as fight, accurate. Now let's test the model again on another unseen video. As you can see in the following video, a person is coming in and collapsing down on the mattress. So the anomaly detected was flagged as yes, and it was further classified into a collapse. This results into show how the model is well trained to distinguish between the type of anomalies. Now let's go and check for another video. As you can see in this video, there is no type of anomaly occurring in the following video. The person is just walking out of the uh, particular complex. So we can see the anomaly detected is no. And as the anomaly is not detected, there is no need to call for the second model for further classification. Thus, this simple UI or the Flask application enables user to test the model and get a grasp of this concept. For the project, we have, as we mentioned in the literature review, we went through a variety of papers. The references are mentioned in the further slides. This is it for the end of the project demonstration. Thank you, everyone.